Okay guys, so just thought I'd do a quick recording of this test for you so that, obviously because we don't have a huge amount of time to go through it in the lesson, do a quick little recap of a couple of more challenging questions and then pick up from where we've taken off. I think this one was probably one to consider. Remember that when it's talking about energy states of an atom, so this is the idea that electrons can move between energy levels in their atoms. And what we know is that electrons get excited and then they fall down, and each one of these represents a way in which they could fall down. So there's 1, 2, 3, 4 different ways. Now the energy given out depends on how far they fall. So we can see that this one here is the smallest amount of energy, this one here is the largest amount of energy. Now energy is equal to hc over lambda. That was done in the photons lesson. So if you're dividing through by smaller wavelengths, we've got a smaller value here, we get a higher energy. If we divide through by a really big value, we get a small amount of energy. So it's asking which transition gives rise to a longer wavelength. So long would mean that this number is big, which means that this would be a small amount of energy. So it is E4 is the answer. Okay. I think this was perhaps a question that people struggle with, so I'm just going to rewrite out the equation. We had a 2,1 hydrogen plus a 2,1 hydrogen goes to a 3,1 hydrogen plus some energy. And what the question is asking you to do is work out how much energy has been stored there. Now, when we're doing that, what we need to think about is, okay, well, what did I have before? And this is the binding energy per nucleon. So this is a 2,1 hydrogen plus a 2,1 hydrogen. So there are 2 nucleons in each of these. So we do 2 times 1.12. And because there are 2 of the same particles, we can just multiply that by 2. So that tells me the total amount of energy that I've got on this left-hand side of the equation, which I can't remember what it came out as, but we'll do it in a second. And that goes to a 3,1 hydrogen. So this is 2.78 per nucleon, 3 nucleons. So we do 3 times 2.78. And when you do the difference between them, that gives you a value of 3.86 mega electron volts. Now, if you can't remember what mega electron volts are, again, go back to that first lesson that we did and have a little bit of a peek at it and make sure that you understand how to convert from joules to electron volts. Now, I'm really hoping that this is recording sound, so I'm going to check it. Okay, hopefully the sound is working, but we shall soon find out. Okay, so this is almost certainly the question that so far had caused the most amount of problems. And perhaps if I rewrite the equation down here, it might be slightly easier to see. We have a K minus plus a proton goes to a K naught plus a K plus some particle Y. And what is the charge? Well, the charge has to be -1 because we know that this has a total amount of charge equal to 0. And at the moment, this is a plus. So therefore, Y must be a -1 in order for this time to be 0. Now the next question is, well, identify the strangeness. Well, this is a strong interaction. And so you know that strangeness has to be conserved. So how do I do this? Well, it's told me that a K minus has a quark structure of anti-up strange. And it's told me that a K0 has a quark structure of K anti-strange. Well, the strange thing about strangeness is it's the opposite way round to what you expect. So a strange quark has a strangeness of -1, and an anti-strange quark has a strangeness equal to +1. And this is given to you in your data booklet, so it's not something you need to remember. You just need to remember to look in the data booklet. So let's think about the strangeness so far here. Well, okay, we've got a K minus, which is up strange. So they've given you anti-up strange, right? So it contains a strange quark. So this has a strangeness equal to -1. Plus a proton, which doesn't have a strangeness, so this is 0. K0, which is down anti-strange. So anti-strange is +1. So this is +1. Plus K plus Y. Now, this is where the challenge comes in, because you need to find a composition of quarks that gives you a charge of +1. And this is given to you in your data booklet. Okay, it's given to you in your data booklet. And essentially, we need to find a combination of a quark and an anti-quark that equals a charge of +1 and has a strangeness. Okay, well, the charge on a strange quark is either +1/3 or -1/3, and that depends on whether it's an anti-strange or a strange quark. Now, therefore, if it's a plus, then we need to think, well, okay, well, what's the first quark got to be? It's got to be an up quark, because an up quark has a charge of +2/3. And so it then must be an anti-strange quark, because a strange quark has a charge of -1/3. So an anti-strange has a charge of a +1/3. And we know that it's a quark-anti-quark pair. So if this is a quark, the other one has to be an anti-quark. And again, this is probably one of the most conceptually challenging bits we've done. So stick with it. So what we've got up here is an up anti-strange. So this has got +2/3. This has got +1/3. So this has a charge equal to +1. So that works, that's nice and happy. But it now contains an anti-strange quark, which if you look back here, this now has a strangeness of +1. So this left-hand side is -1. This right-hand side is currently +2. So what does Y have to be in order to equal -1? Well, to go from +2 to -1, this must be -3, because 1, 2, -3 goes to -1, so then it works. So this quark over here must have a strangeness, sorry, this particle over here must have a strangeness of -3. Potentially, I mean, this is one of the hardest questions in the entire course, but hopefully something that you stick with. Oops, got an email, just check. Oh yeah, oops, better do that. So now we get into some stuff that hopefully is okay. This is all about radioactive decay, so go back and have a look at the half-life lesson if you need to. Outline how the count rate was corrected for background radiation. So count rate is the number of decays being given off by radioactive nuclei. So if we were to think about the total count rate measured, it would be equal to the background, which is examples of background radiation can be rocks, medical waste, cosmic rays. It would be background plus the count rate from the source. So the count rate being given off by the radioactive thing. So what do? Well, you just subtract your background rate from each reading. So what that means is, if I had say I was looking at my Geiger-Müller tube and I had 100 counts on there, and I knew that my background rate was 20, I'd do 100 minus 20, and that would tell me that I had 80 left overall. When a single piece of thin copper is placed between the source and the detector, the count rate is 810. So we go up to here, it's somewhere around there. The foil is replaced with something that is 3 times as thick. Estimate the new count rate. So what you know is that thickness is going to be somewhere around the 0.25 mark, about here. Oh, I've done a terrible drawing, but I should have drawn it. It should be about here, so I'm not sure if you can see that. So it's about 0.25, and that equals 810. So it's now been replaced by something that is 3 times as thick. So something that is 3 times as thick is going to end up being at 0.75, which is up here. You go along and you read off the graph, and it's somewhere between 350 and 420 was your allowed rate. When I did it, I got 390. So you got 1 mark for getting the value, and you got 1 mark for the graph. So hopefully a nice easy 2 marks there. We then move on. I know this is a question that caused a few people a challenge, so and I think it's possibly around what this point means. So comment means, well, explain what you've got going on. Apologies, it just appears to have gone blurry. Yeah. So we know that we've got copper and we've got lead, and it says further results were obtained in this experiment with copper and lead absorbers. Comment on the radiation detected from the radioactive source. So they want to know about the radiation, make a comment about the radiation. So what can we do? Well, we know that when we went from copper to lead, the count rate went down. Okay, it didn't stop completely because it's not 0, but it went down. But we also know that there was some radiation going through when it was copper. So there are 3 types of radiation. There are alpha, beta, and gamma. We know that this is stopped by thin paper or air. We know that this is generally stopped by aluminium, and this is barely stopped, but is stopped a little bit by lead. So if this radioactive source was alpha, then this value would be 0 because no radiation would get through. But it does, some radiation gets through. So my first point would be that there is no alpha because radiation is getting through. Is getting through. My second point would be, well, okay, well, what's happened here? The radiation's gone down. Sorry? So there must be some beta because radiation is getting through. Okay, there is beta, but there is also gamma because it's getting through the lead. There is some getting through lead. So if there was no beta in there, then we wouldn't expect to see this drop. Okay, we wouldn't expect to see this drop. I would probably finish with something like lead is a better absorber than copper, and because the reason why we know that is because we can clearly see that the lead managed to stop more of the radiation than the copper did. Okay. This question is knowledge recall, so it's asking for a decay equation from there. You have to recognize that the proton number is going up, so this is an example of beta decay, specifically beta minus decay. So 137.55 CS goes to 137.56 Ba plus 0 minus 1 beta particle. This is an electron, so we have to have an anti-electron neutrino. Got 1 mark for getting that, 1 mark for getting that. Knowledge recall. Not much I can do there. So it's really rude. Can do something. Come and see me if you don't understand it. And then finally we get on to perhaps where some people struggled. State the quark structure. So you could do quark, anti-quark for a meson, and then quark, 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 or quark, 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 anti, anti, anti for a baryon. So you'd need 1 mark for that one, 1 mark for that one. And you have to get both of these for that second mark. So this is perhaps where people were needed a little bit of support. So it says explain which interaction. So you could either have strong, weak, electromagnetic, or gravitational. Those are the 4 interactions. And what we've got is here, we've got a strange quark going in, and we've got an up quark going out. If there is a change in quark, then you may remember I talked about this being a change in flavor. And it is the weak interaction that is responsible for that. So it is a weak interaction due to the fact a quark is changing flavor. Okay. So if you see one, like you started off say with a down quark, you end up with an up quark, or you got an up quark going to a down quark, strange to an up, whatever it may be, if the quark on the left is different from the quark on the right, that's a changing quark flavor. And then that is the weak interaction. So this is the exchange particle. And remember, there were in the weak interaction, there were three possibilities: W minus, W plus, or Z0. And so what we've got to do is make a decision. Well, okay, this was a strange quark, and this was an up quark. What's happened here? Well, if you look at your data booklet, a strange quark has a charge of -1/3, and an up quark has a charge equal to +2/3. Hello, sir. I am making a video, so you'll be on it. That won't be very long. So you've got the charge going from something negative to something positive. So if you're going to become positive, you have to lose a negative charge. So in order for this quark here to lose a negative charge, this must be a W minus, because that indicates that a negative charge is being taken away from there. So hopefully that'll do. Now, perhaps something that you didn't do here, if you've got these arrows indicate the direction in which the particles are moving. So we can see we've got a strange quark going this way to an up quark, down to a down, up to an up. None of these quarks from here are anti-quarks, so all of the arrows go left to right. If it's an anti-particle, the arrow goes the opposite way around. So this is a normal particle, so we put the quark in that direction. But because this is an anti-quark, we draw the arrow in the opposite direction. I think we're there. Done that because I just spoke about it in the previous question. And what is the benefit to multiple countries doing this? It costs a lot of money. So if you've got multiple countries doing it, then you split the cost. So a little bit of kind of a wider context question. Cool.